So thank you all for coming to my presentation. This year, my research study was on using high throughput virtual screening of TAAR1 for anti-schizophrenic drug discovery. So first, to give some context, and then this is just the TAAR1 receptor we used this year. So to kind of give some context to the research study, we'll start off what is TAAR1. So TAAR1, also known as trace amine associated receptor 1, is a type of G protein coupled receptor that's mainly found in your brain. The type of ligands that actually bind to TAAR1 are known as trace amines. An example of an amine can be seen on the board here. It's just a type of nitrogenous functional group. Actually in the brain, trace amines are considered a type of neurotransmitter that are generally found at lower concentrations compared to other neurotransmitters, and they actually bind to TAAR1. So, in recent research has actually shown that TAAR1, the receptor, actually has somewhat of a modulated capacity, meaning it can serve as a regulatory receptor to control neurotransmitter release as well as neuronal activity. So, recent studies have also shown that it has major involvement into the release and control of neurotransmitters like serotonin, dopamine, and glutamate, which, little backstory, those are like the major neurotransmitters in your brain that have a lot to do with facilitating like neuronal communication. So with recent studies showing TAAR1's regulatory activities, it's been, along with its involvement in like major neurotransmitters in the brain, it shows evidence toward its further involvement in mood regulation, cognitive function, and reward circuits. So because of its involvement in these three major parts of your brain, it shows potential into the polypharmacology for the treatment of many mental health disorders. And this is what kind of this study was geared around. So kind of getting into the goals and potential of TAAR1 for this specific research study, I first want to get into how we targeted TAAR1. So almost all prior research has targeted TAAR1 via agonism. So agonism is an interaction at the receptor site where a ligand binds to the receptor and elicits some kind of stimulatory or excitatory response. So the purpose of this research study was to find an agonist ligand to bind to and activate TAAR1 to aid in drug discovery for the mental health conditions of schizophrenia and methamphetamine addiction. So starting off with methamphetamine addiction, you can see the compound labeled meth here. So meth is also known as like a highly addictive opioid that actually binds to and stimulates TAAR1. When it binds to TAAR1, it causes this influx of dopamine in the brain, which is associated with the formation of addictive pathways, as well as the like euphoria feelings that are associated again with methamphetamine addiction. However, recent research shows the potential of a TAAR1 agonist binding to TAAR1 in the use of addiction medication and health, because it will stimulate the receptor, but it won't cause that influx of dopamine that creates, once again, the addictive pathways. Moving into schizophrenia, which was kind of more the center of this research study, a TAAR1 agonist again shows potential into alleviating the symptoms of schizophrenia because it would theoretically correct the dysfunctioning and dysregulated neurotransmitters that ultimately cause psychosis. So this is another area of potential for TAAR1. So a lot more research needs to go into the use of TAAR1, especially with how many bad side effects for a lot of antipsychotic medications that are on the market right now. There are a lot of unfavorable side effects. So it's really important to further investigate TAAR1 as an alternative receptor to target. And I just kind of want to go over some of these ligands over here. So this one, once again, is methamphetamine. This one is actually something called an endogenous ligand that binds to TAAR1. It just means it's a ligand that's naturally made in your body. And these last two were synthetically made in a lab. I just wanted to show these because you see the consistency of the amine group, the nitrogen right here, whether it's protonated or not. The consistency of that, because that's going to be really important in defining a ligand that has a high affinity for TAAR1. So now that I've kind of gone over and given context on what TAAR1 is, I want to get into beginning methods of the research study. So the beginning methods for this study can be generally split into two parts. First was finding the receptor grid we wanted to use, and then second was finding the ligands we wanted to dock to this receptor grid. So the receptor that we used, we found on something called the Protein Data Bank, which is a website that just houses a lot of crystal structures for receptors. This semester, we actually worked with a research group at Sichuan University in China. They're the ones who kind of picked out the receptor that we used. They picked out this receptor because it was a larger receptor, so we can not only dock more ligands to the receptor, but also bigger ligands. And a bigger receptor also avoids something called the collapsed binding pocket effect, where the receptor kind of like folds in on itself. So once we had the receptor, the next step was finding the ligands we wanted to dock to this receptor. So we used a website called Zinc20, which, like referenced in the other presentations, just has a lot of different molecules that dock to receptors. So we had a variety of criteria we were judging our ligands on, but the major criteria that we absolutely needed was that all molecules had to have a +1 or +2 charge. So this is because of a really important interaction that actually happens at the binding site. It's called a salt bridge. It can be represented by this kind of pink dashed line right here. Basically, a salt bridge is when the positive charge from the protonated amine from the agonist or the trace amine creates this really strong, not necessarily a bond, but more of an interaction with a negatively charged molecule in the receptor site. So this just gives molecules a higher affinity for TAAR1. So this was a really important criteria that we needed when looking for a ligand that would once again have a high affinity for TAAR1. So after all this, we had a really big screening of 211 ligands to bind to TAAR1. So obviously we had a lot to do. It was a really, really big research study, again, because this is more not necessarily exploratory, but in its beginning stages. So now that I kind of have the beginning methods, I want to begin to get into how we docked these to the receptor. So once we had the designated ligands and receptor, we loaded them into an online program known as Maestro. So once we loaded them in, we had 3 screenings that we used that would basically dock all of 211 of these ligands to the receptor. So the first screening we used was HTVS, which is kind of like a more general screening, and then we had a cutoff docking score for the ligands. The surviving ligands would then move into the SP screening, which is a little more strict, and then finally the XP screening, where we had a slightly more strict docking score cutoff. So the reason we kind of went from the least rigorous to the most rigorous screening is because mainly of computational times. So if we tried to throw 211 million molecules into the strictest screening, it would probably take years to finish. So we kind of had to start with a more general screening, kind of get out like the duds and the ones that wouldn't really make it quite far, and move the important ones to the more strict screening. As you get into the strict screenings, the ligand-receptor interaction begins to mimic more of what would actually happen in the body, meaning when a ligand docks to a receptor, it goes through the receptor goes through like this conformational change around the ligand. So as you get into the stricter screenings, it becomes a little more accurate into what would actually happen in the body. So after screening, all the molecules that were left after the XP screening or the most strict screening signify having a high affinity for TAAR1. So now that we screened the molecules strictly based off docking score, where we had about 20,000 molecules that passed that test, we now had to screen them and sort them based on variables specifically that have to do with how the drug reacts in the body. So the variables that we filtered by were something called hERG, which measures toxicity, so how toxic the molecule is for the body, CNS, so how well the molecule crossed the blood-brain barrier, and then oral absorption, how well, if it did become a drug, it would be absorbed into the body. And then lastly, STARS and EULA-5, which are 2 kind of umbrella filters that take like multiple things into consideration, like docking score and molecular weight and such. So after this second part of the screening, we went from 20,000 ligands to 704 ligands. So 211 million ligands to 704 ligands is a huge jump. We obviously did a lot of filtering. I'm not going to sit here and show you every single one of these ligands. So instead, we kind of clustered them into groups based off of their chemical structure, where we got kind of general scaffolds and to get kind of the best generalization or best scaffold for a potential drug. So moving into the results, finally, after months of screening, these are the top 3 contenders, the top 3 scaffolds that we had after all of that screening. So number 1 here is like the best. The other 2 are good, but this one is like the best one that we found. It has the best docking score, the best or the lowest toxicity, the best oral absorption, the best CNS. But again, all of these are good. There's just a couple commonalities I want to point out within these drugs. So you have the presence in all of these of something called a carb amide. It's basically this carbonyl group with the nitrogens. It's kind of like right all in the middle of all of these scaffolds. Just an interesting something to take notice of. And then also, all of these molecules have a charge of +1. So again, the positive charge is really important for that interaction, the salt bridge at the docking site. Unfortunately, all of the positively 2 charged molecules were filtered out because of their size, which is unfortunate, but we still have that +1 charge, so that's really important. And then I also just want to comment on the presence of a trifluoride group coming off this carbon in the first one, the absence of a trifluoride group in this one, and then once again, presence of a trifluoride group, and then also like an extra little fluorine right there. So just some interesting things about these general scaffolds. So now that we have the scaffolds, I kind of want to talk about the future directions with TAAR1. As much as we did with this semester, there's still a ton moving forward we can do with this receptor. So our plans that we already did is we sent these scaffolds that we made this semester to the research group at Sichuan University in China that we're collaborating with. They're going to run something called biochemical assays to determine more in depth the activity of the ligand at the receptor site. So once they send us these results, next semester we'll be primarily looking at and analyzing the ligand to receptor interaction using induced fit molecular docking. This is an even more in-depth analysis of how the ligand will behave at the receptor site. This is because the current 3D models we're using now are accurate, but they don't exactly mimic what would happen in the body. So proteins are a lot more fluid than what is represented in these 3D structures. There's a lot more movement and fluidity at the receptor site. So induced fit molecular docking actually takes this fluidity and movement into consideration rather than 3D models which kind of freeze the protein in time and just put it on the receptor. So this will be a lot more accurate to what will actually happen in the body. So we have a lot more to do next semester with TAAR1.